Hi, Mrs. Gates here. The purpose of the activity we are going to be working on today is to develop some intuition about graphs of accelerated motion. So when an object is accelerating, what will the graph of position and velocity look like? We are going to be using a couple of lab supplies. I have some frictionless dynamics carts, which just means that they are these carts that sit on these tracks and move back and forth with basically no friction. So they're not going to be slowing down or whatnot on their own. We will be tracking the motion of these cars with one of these Sonic Ranger motion detectors. They send out little pings of sonic waves. It bounces off an object and comes back. And then this Sonic Ranger is able to record the position and velocity of an object as it's moving. The objective for each one of these 5 activities is for you to watch the motion of the car rolling down the track, either speeding up or slowing down or bouncing off the end, and predict what the graph of position and velocity are going to look like. We'll then show you the graph of the motion in real time as the car is rolling, and you can check to see if you were correct. For each one, stop the video and take as much time as you need to make your predictions, and then stop the video again once you see the correct graph and try and figure out where you were right and where you were wrong. Good luck and have fun. Notice that the slope of the position time graph is constant in 2 different sections, and that the velocity graph has 2 horizontal sections. The slope of the position time graph tells us the velocity, so we can find the velocity independently for these 2 regions of the graph. The next motion you will look at is the car rolling down the ramp with the motion sensor at the top. The motion sensor collects data as if it is at the origin and moving away from it is the positive direction. Pause the video and make your prediction. Since the slope of a position graph is equal to the velocity, as the car sped up, the curve on the position graph got steeper and steeper. The velocity graph increased with a constant slope. The slope is its acceleration, which in this case was 1.142 meters per second per second. The next motion we will investigate is the car moving down the ramp with the motion sensor at the bottom. How will moving the motion detector change your graphs of position and velocity? As the car sped up, the slope of the position graph got steeper and steeper, but this time the velocity was negative, starting at 0 and increasing at a linear rate. Again, the slope of the velocity graph is equal to the acceleration of the car. In the next case, the car will go up and down the ramp with the motion sensor at the bottom. It will start with an initial velocity going upwards. Pause your video and make a prediction. In this case, the position started near 0, went up, and come back down. Notice that the peak point on the graph lines up exactly with where the velocity was equal to 0. And notice that the velocity had a constant rate of change or acceleration during the entire motion. In this last case, the car will again go up and down the ramp, but this time with the motion sensor at the top. Remember, the motion detector is the origin. Pause the video and make your predictions. The position time graph is again parabolic. Notice that the peak of the position lines up with where the velocity graph crosses the x-axis. That means that at the top of the motion, the velocity of the car was 0. We can find the acceleration again by finding the slope of the velocity time graph.